Welcome, everybody. Welcome, welcome. How's it going?
Hey, Vlad. How you doing?
Good, good. How are you?
Doing pretty well. Looking forward to this review session. You're probably going to save quite a few people's grades with this cookies and cram, hopefully.
Hopefully. So I'm going to tag a few people, make sure they come.
I try to promote the session on like first year WhatsApp groups, and hopefully people actually attend. People seem
so.
genuinely interested.
So at 5 o'clock, I'm going to send out a message tagging everyone. And then at 5:05, we're going to get started. There's a lot of people in the ELG one right now. Pretty crazy.
Yep, I've seen that. 37. That's quite a few people.
37.
Which ELG course specifically?
It's either 2136 or 2137. I think it's 2136.
That's circuit theory 1, right?
No.
That's electronics.
Is it? I think it's electronics 1.
Okay.
So I'm going to be recording this. If you don't want to be in the recording, then either tell me and I can cut you out if you do speak, or don't speak at all, and then you won't be in the recording. But if you do speak and you don't tell me anything, I'm going to assume that you pressed OK on the recording thing and that you are consenting to being recorded. The recording is going to be posted onto our YouTube, the IEEE YouTube, and then I'll share it once it's done uploading. But that would probably be done uploading either tonight or tomorrow morning, depends on when the processing is going to be done. And then Nick is going to post it. So at 5 o'clock, I'll send out the @ here, and then at 5:05, we'll get started. When's this exam?
The 26th of April.
26th of April. Wow, that's quite a bit away. Who knows? Might have to host another one of these, just like I did for Python.
That would be dope. I would attend that one too.
If it's too far away, because all my hardest exams are going to be done by the 21st. So I might be able to host another.
By hardest, I assume you mean control systems, right?
Yeah, control systems.
Yeah, I've heard some feedback from that class. Definitely not the one I'm looking forward to the most in my course sequence.
Pretty difficult. It's doable, I think, but a lot of things to remember. Alrighty.
Quick question. Are we going to go like in order of like how different concepts and like data structures were covered in the course, or is it going to be random?
It's just going to be like a general breakdown. And then if you have any questions about them, we can go and look at them further. I only have 2 hours today, so I can't go too much into detail. But what I can do is either move this to Discord after and then go more into detail, or yeah, we'll just have to go to the questions.
Understandable. Sounds good.
Hey, what's up? So I'm gonna do the @ here right now. I had a few people ask me if I could post that. 5:05, we'll get started with the presentation. I'll just share that quickly. There we go. I'm hoping everyone can see that.
Yep.
I mean, it's up to you. I usually don't write notes in any of my classes. There will be a code along though. So if you want to open an IDE before we start with that, you can do that. Can you share the PowerPoint? Yes, I can. Just give me a sec. I'll share it as a PDF. There it is. $16 people, not bad. There might be more people coming as we go. And then if you guys have any questions at all, don't be afraid to interrupt me or type in chat and I'll answer those. What screen do you guys see?
The presentation one. Like
the presentation?
Yeah, not the not the actual showcase.
Okay. So this right here, where my mouse is?
Absolutely.
Okay. So I'm running on 2 screens right now. And it's being pretty weird. It's using my second screen as the default.
I think you have an option that's called swipe displays. Yeah. Yep. Now it's the good one.
No, it's the good one. Okay. Okay, so you were seeing that one. Okay. What time is it? 5:04. We'll get started in 1 minute. And then if more people come, then we'll just keep going. One more person, that makes 19. It's pretty good. Okay, so the way we're going to do this is first, there's going to be a presentation, a short breakdown of some important and later topics that you guys went on in the course. Then we're going to do a code along for the previous April 2020 exam, part 2. And then there's going to be some more theoretical questions for the Kahoot. And whoever wins that Kahoot gets a $5 Amazon gift card, and you're crowned the champion of ITI1121. And so let's get started. We're going to start off with the presentation. Welcome to Cookies and Cram, ITI 1121, Introduction to the World of Java. So some important stuff that we're going to cover today. First is going to be exceptions, and in particular, custom exceptions. Then we have the stack and queue architecture. Then we're going to talk about the linked list and the double linked list. Then we have iterators and binary search trees. And once again, if there's any questions as we're going along with these, don't be afraid to interrupt or ask your question in the chat. So first thing, we have exceptions. These are throwable objects that notify the program or the programmer of an unexpected or disallowed event. So you throw these whenever something that isn't supposed to happen happens. For example, you have array out of bounds exceptions if you iterate over the limit of the array or an index that doesn't exist. And Java native exceptions exist, just like the one I just spoke about, but you can also create your own by extending exception. And so here's an example of that. I made a test exception that extends exception. And then the first constructor here is usually what you're going to use. So it creates the exception, and then you put a string message. And then the second one here, you're probably not going to use it in this class, but you're able to throw a stack trace in, and then it prints out the stack trace instead of just the message. So it's what you see usually when you debug things. You're able to click and see what lines caused your error. That's what a stack trace is. So next we have our stack, and how this works is first in, last out. And so imagine a physical stack of items where you only have access to the top element. And something that you can think about here is the Pez Dispenser. And believe it or not, before COVID, the professors actually distributed a Pez Dispenser during this class. And then we were able to take the candies out and eat them, but we were only able to access the top candy, the one that we were dispensed. We had no idea what the other ones in it looked like, and we couldn't take those ones out. And so it's used in many applications, including hardware, recursion, or even the stack in when you're programming, like Java and Python. So the common methods, the most used methods are Boolean empty, which tell you if your stack is empty or not. You have element pop, which gets the top element out of the stack and then returns it. And then you have void push. So that takes element as a parameter, and element could be anything. That's just a generic. So that puts it onto the top of the stack. And remember, once you have a stack, you can only put things onto the top and take off that same top object. So first in, last out. Next, we have the queue. This is a mistake here. It should be first in, first out. Just like that. First in, first out. Now imagine a lineup of people outside of Loblaws, just like we had during COVID. So the first person gets into Loblaws first, unlike a stack where the last person would get in first. That would make sense for a line. And these are also used in several applications, such as your Spotify or Apple Music queue, your queuing network requests, like if you send up a request, the program or the server receives that request, and if it can't respond to it immediately, it puts it up into a queue, and then first in, first out, whichever one comes in first gets taken out. So the common methods here are empty, same thing as the stack, tells you if your queue is empty or not. You have add, which adds to the end of the line, and then you have remove, which removes the first item that has been inserted into the queue. So next, we have singly linked lists, and these are abstract architectures, which means they're not really contained in an array. You sort of have to keep track of the elements on your own, or the program does. And the way these works is these items are connected through pointers. And so in a singly linked list, you only have one connection per element. So in this example here, you have your element, and then that element is only aware of the element after it and not before. And these can be used to implement a queue or a stack. Actually, no, these can be used to implement a stack. Actually, or a queue, yeah. If the arrow is the opposite way, that could be a queue as well. And then the advantage over doubly linked lists is that it takes up less space. So each element only keeps track of one other element, and it doesn't take as much space as keeping track of both of them. So then you have your doubly linked list, and this is an abstract architecture where elements are connected through pointers again, but this time you have two connections per element. So you have your next and your previous element. And so this is just an example of a doubly linked list where every element is aware of both the next and the previous element. And so you can implement binary search trees using sort of doubly linked lists, how they expand. You can implement sparse vectors, as we're going to see in the example today. You could do doubly ended queues. You could do Circular lists, say here, instead of null, you would circle all the way back to the end. And you can also, and you can also do circular queues. And the advantage here is that you have more knowledge and more back and forth movement within the elements.
I do have a quick question concerning doubly linked lists.
Sure.
Usually the common methods are, to my knowledge, adding an element to the end of the doubly linked list or adding an element to the start of the doubly linked list. Are there like any other common methods that
Yeah,
we
you
should
usually have
be familiar with?
Yeah, you have get. So it iterates throughout the linked list, and then it gets whatever index or value that you want. You have add, of course, add to the end, add to either end, and then you also have remove. So removing would be removing that element, and then the elements that are around it, you now link them both to the new element that you put, and that element that you just entered, you link that one to the two that were linked before. And so those are the most common one. What about dummy nodes? You can use dummy nodes, or you can use nulls. You can use nulls instead of dummy nodes. Dummy nodes are basically nodes that are just there to start the linked list, and they're technically not a part of the actual linked list. They're just there to represent that they are nothing. But you could also use nulls as shown here.
A quick question concerning the null for like the head of the doubly linked list. Usually it's in the constructor for like it's in the constructor. Like for example, like of like the node, like you say this dot like previous would be null, right? Okay, thanks.
Yeah, it's if you don't assign it anything yet, not even in the constructor, the default value is null if it doesn't have an assignment.
I see. That's good to know. Thanks.
So yeah, if you don't do this dot previous equals something, then it's automatically going to be null. So in what situations would a dummy node be useful instead of just null? We have one in the example where the dummy node always has next as itself when there's nothing in there. And so you don't really have to create your own head. And circular lists, yes, that can use a dummy node. That's what the sparse list is going to use. And so it links back to itself. Do you have to use dummy nodes to know where we reach the beginning? Yes, that's an easy way to implement knowing the beginning and the end. Just when you've reached the dummy node, you know that you've reached the end of the queue or the list. Are there any more questions about doubly linked lists? Okay, we're going to move on to iterators. And iterators are custom classes or architectures that help a programmer iterate over your custom architecture with ease. And now you might think these are kind of useless in your own assignments because you're the only one coding them. But these are super generic, and anyone without seeing your code can use these, and they should know how they work because they are generic. And these two methods that the iterators contain, the two main methods, are hasNext, which is a Boolean telling you if you've reached the end of the list yet, or next, which gives you the next element in the list. And so this is super useful when you're working in teams and someone without reading your code wants to use it and doesn't have to create their own iterator, because different abstract data structures can sometimes have different ways of iterating over them. And if you don't want to do that manually, you create an iterator and it makes it easy for people. That's the main use for them. Or it makes it easier for yourself if you don't want to recode manual iteration every time. So the last thing that you guys went over is binary trees. And binary trees are the backbone of several architectures, including heaps. Some database structures are made using these. Binary search trees, as shown here. This is a binary search tree. You have peer-to-peer programs, sometimes use trees to communicate with each other. And some compression algorithms use trees as well to compress. And so you use recursion for traversal. And three main methods that have been learned are pre-order, in-order, and post-order traversal methods. And we'll actually go through those. And so that's it for the presentation. Are there any questions before we move on to the code? Any data structure that you want to elaborate on or other questions that I haven't covered? If not, then we should be good to go. I'm just going to share my IDE here. There we go. So I'm going to give you guys a little bit of time to open up your own IDE if you want to code along with me. And if not, then we'll get started. So the first thing before we actually get on to the questions is I want to show the initial steps for coding a binary search tree. And then we can go on to make the different algorithms. So the first thing in a binary search tree that you're going to want to have is your element or your node. Here we're going to call it element. So we're going to make a private class called element. I got someone joining here. So we got private class element. And then this doesn't really have a type right now. And then usually in a search tree, your element has 3 values. And for our first value, we're going to have an integer called value. Our second is the left node. So we have private element left and private element right. And then for our constructor, we're going to do public element. And here we're going to have nothing. Actually, no, we're going to have a value here. Int value to create our first element. And then we're going to do this dot value equals value. So we're setting the private variables, the instance variables of the element to be the parameter that we put into our constructor.
Quick question. Of course, the value for the element can be anything but an integer. It can be a string. It can be anything else, right?
Of course, yes. Okay. But for this one in particular, we're going to do we're going to do integers. And if you do a binary search tree, usually you have integers because you want to know which value is larger and which value is smaller, unless you have a comparator. But in this case, it's just going to be integers. And element does not need to be static because it's a private class that we're only going to be using within the binary search tree class. So it's a nested class and it does not have to be static because we create instances of it and we don't use it for its methods or its variables in particular. Static is when you want to use class variables and class methods. And when it's not static, it means you can just create instances of it. Alrighty, so here for our binary search tree now, we're going to have the private element root, and we're also going to have the private Boolean empty. And this is just going to keep track of whether or not our binary search tree is empty. And then usually what I go do is I create getters for these. So public Boolean is empty. We just generate that. And then public element get root, we generate one of those as well. Just in case we want to use them later from a different class, makes it easier. And so the next thing that we're going to want to do is insert items. And since this is a recursive method, since we have to look through the binary search tree to know where to place our elements, we first make a public void insert with just the value that we want to insert. And then we also make another method, public void insert. Here we do int value, and then we have element to know which element that we're at in our recursive function. Does that make sense to everyone? So this is going to be used in our main method when we just want to insert value, and then this is going to be used in the recursion. And so here we can just straight up call this insert value, and then here we're going to do root. So this dot root, and that's the element that we start with. And so here for inserting, the first check that we want to do is if this is empty, if our binary search tree is empty, that means we don't have a root yet. So this dot root equals new element with our value, and that's it. And now, of course, we want to do empty equals false, because now it's not empty.
Quick question. Usually that's the only like edge case when you know, adding nodes to a tree. It's if the like it's already empty. That's the only one, right? We have to worry about.
It depends on how you program it. Here, our only edge case based on the way that we're programming is if it's empty.
Okay, makes sense.
But sometimes you can have a max value, like you don't want your binary search tree to exceed some amount of values, or your binary search tree has too many elements on a single branch, and that could also be an edge case, and you kind of want to reorder it maybe.
Sounds good. Thanks.
But for this, for our simple insert, this is going to be the only edge case that we encounter.
Sorry, so you set empty to false, but it doesn't have a default value. Should it be true, or do you have to do that in the constructor?
Good catch, good catch. So here we're going to have public. We're going to make our constructor binary search tree, and then for our constructor, we have this dot empty equals true. Good catch.
Sorry.
Yep.
Are we taking null? Are we taking null elements in the insert?
No, we're not going to be taking null elements. But I'm just not going to assume that that's an edge case for now. I'm just going to say they are integers. And whenever you do have an assumption, usually write it out like this. Assumption int always has a non-null value. Non-null int value.
Vlad, I got a quick question. For the if statement for the edge case, shouldn't the condition like in the if statement like contain like a double equals true or
right here?
Yes.
So this right here is a Boolean in and of itself. So if you do this equals true and say empty is true, right? You're saying if true equals true.
I see. Okay, that makes sense. Yeah.
As long as you have a Boolean in here, that's all that matters.
I see what you mean. Okay, that makes more sense. Thanks.
And so that's going to be our only edge case here, just to keep it simple and to get things rolling. And so next, we're just going to do else. And then else, here we have if current element, if the element equals, or I mean is less than the value that we want to insert, then we place it to the left, or we go to the value that's at the left. So we do current or element dot right equals new element, and then we put our value. Do you guys notice anything wrong here?
Element dot right
Does it make sense?
already have another element.
Exactly. Exactly. So this won't be right because what if element.right already exists? Then you're just going to be basically chopping off the existing branch and placing your new value in. And we don't really want that. So we're going to have another check here. We're going to say if element.right is null, then we do this. So if we don't already have an element to our right, then we insert a new one. But if we do, then what do we do?
Could it like be at the same like initial if statement with like an AND operator? So like if element dot value smaller than value and element dot right equals null, and then like put the content of the if statement there, or that would work too.
It could, but that would be a bit more if statements because here we're generalizing it if it's less than value. And then here we're going to have an else here. So if it's more than value, we're going to do another set of operations. Yeah. So as the comment says, we're going to have to go deeper. How do we go deeper into this? So our right element is not null. We have to go to it. Samuel says recursion, but how would we implement recursion here?
Making a call to the function.
Exactly. Call to the function. So what would the code here be? Insert. What do we insert for value?
The I would guess element dot right, or nah.
So value would have the same value.
Yeah, the value would be the same.
Inserting the same value. And then here, oh, that's not what I wanted. And then here, right, you do element dot right. And so that goes all the way back up into here, but with the new element. Same value, new element, does the same check. So is that good for the right side? Or is there anything that we missed?
I feel like we're good. I'm not sure.
Feel like we're good? How sure are you about that?
I think we've covered like the most prominent edge case if element dot right is null, but I feel like I'm missing something.
You have to be certain.
I'm never certain, especially not on the file.
It is done, or does anyone have a certain answer for me? Are we done? Can we move on to the right side or the left side?
I guess we could be done, assuming the left side will be done after. So.
Right.
Yeah.
Right. So you're certain about that?
Yeah. Yeah.
Okay. That is correct. We are done with that. So now we have the left side. And so for the left side, we do if element dot left is null, then we insert an element into element dot left. So we create a new element with the value and we insert it to the left. But what if it's not null? What do we do?
We make the exact same recursive call as the element dot right, but this time it's with element dot left.
Exactly. So we're going to insert value element dot right. And just like that.
Shouldn't it be element dot left?
Right. So are we done here? Or is there just one more thing that we need? What if the values are equal? That's an interesting perspective. What if they're equal? What do we do then? So here we'd put if element dot value is greater than value. Just got someone enter. Is greater than value. And then here we have another else edge case. What do we do if they're equal? Where do we
Would
put
we
them?
just replace the I think it's called like the mother node instead of like I'm not sure, like replacing the node itself by like another one with the exact same value?
Would that really make a difference? That's the same node in that case.
Yeah,
Just
so
not
like
do anything.
yeah, that would make it obviously like what I just said is redundant, but like
Mhm.
Do
Else
so
you can return, or you can treat it as a value that's less. There's several different ways of doing this. I don't know if you learned a particular way, but you can just not do anything if you want to have all your values. I mean, you can put duplicate values, or no, you can't. Okay, yeah, in this case, you would just return, and that's one way of doing it. Or just not do anything. You can just remove this else, and then it's never gonna happen. But for now, to make it more clear, we're gonna return.
quick question. Is this like the kind of situation in which like we have to like throw some kind of custom-made exception?
Custom
Not
made
really.
exception for this, if the value is already in it.
Yeah.
I mean, you could. Let's do that then. Let's create a new Java class. We're gonna do element exists exception, just like that. So here we're gonna extend exception. We make our own exception. So does anyone remember what we do in this case? How do we create an exception?
we create the constructor with a string as a parameter.
The string as a parameter. Just like that. And then what do we do here?
We have to call super.
Super and message. That's right. So we inherit that, that constructor, and then what it does is throw the exception at the exception level. And so here we can say else if they're equal.
Throw and like the name of the exception.
Right. So we throw the name of the exception like this.
I think that's the syntax. I'm not sure.
Brackets.
What do we do here? Brackets?
Is it like the try catch block, and then like if the error is like caught, then we can throw the. I'm not sure.
No. An exception is an object, just like any other class that you would use. It has its own object. So you create an instance of element exists exception, and then you put your message in. So element already exists in the tree.
Right. Now I remember. We did a similar thing in our fourth assignment.
Yeah. And so what's the error here? Why do we still have a problem?
We need to add throws.
We need to add throws? Where?
Beside insert and like beside the function. Yeah.
Right here? Throws,
Yeah.
element exists, exception. There we go. Now we have a problem here. What do we do here?
A try catch block.
Do we want to put the try catch here? Would that make sense?
we would do a try catch in like a main though, right? Or something where we want to see if like something is being caught by the exception or not.
Why would you want to do that instead of just putting it here?
Because if you do it in like a main, you're capturing, you're just doing every single possible, you're just accounting for like any possible input.
Yeah, so basically here, if you put the try catch here, you're not really going to know what the exception is when you're actually coding the program. And so here, you're going to want to do throws as well. Element exception. Element exists exception. So you don't want to catch it in the actual function for your binary search tree. You want the programmer who uses your binary search tree to decide whatever they want to do with your exception. They can try and catch it. And then the programmer that uses this will then decide, okay, we got an element exists exception. What do we do here? Do we keep going or do we stop? You don't want your actual data structure deciding that for the programmer. So does that make sense?
Yeah, sounds good.
All right. And so now we're going to make 6 functions actually. So 3 recursive functions and 3 functions that call those. And those are going to be the traversal methods. And these are just going to print to keep things simple. So here we're going to do public void in order. And then we have public void in order. And then we have element. Just like that. And so here, since these are recursive, like I said, we're gonna have a call to the other in order. And this is gonna be with the root as the first one. Should what be private? The second in order. Right, could be private. Why could this be private? What about the second insert? Yeah, this could also be private, right here. Because you don't want anyone but the main to use the method. What do you mean by the main? The main method won't be able to access this. And it's not because element is a private class. Yes, it's because only this class is accessing it. You don't want anyone else accessing that because they don't need it. This is just a helper method for the actual in order. And so here for in order, if we just want to print the elements, how do we do in order printing? Does anyone know?
Yeah, it would just be like the values of each node, but like in ascending order, not necessarily following like the branches of the tree. If that makes sense.
So how would you program that? If you want to print
No idea.
them in the... No idea?
Nope. I've actually never implemented an order. I guess it would be just
Yeah, give it a go. Start
Okay,
from
so
the
like-
most right and make your way left. Okay, how do we do that using?
okay. First of all, I guess I would go with something like the current node is not null.
Okay,
Well, no, we're making a recursive call here.
if element is not null, like that.
Yeah, and then I would.
Vlad, I'm sorry to
Yeah.
intervene, but I feel like before jumping right into code, you kind of it's good to have like a fundamental base to
We
know.
already went through that.
Oh, okay, I'm so sorry.
Yeah, and the lectures that I'm pretty sure in your lectures you guys had the theory behind this.
Yeah.
So now we're actually.
Yep.
But we went through the fundamentals of trees
Yeah,
in
so-
the presentation.
Yeah, I was just going, okay. I came late. I'm sorry, guys. Go on.
Yeah, no worries. Okay, so if the element is not null, then you do here
A
uppercase
recursive
says
call.
in order.
Right.
Element left. Okay. And then what?
Else,
And then print its value. Okay. And then
Another recursive call, this time element dot right.
yeah. Not this dot element dot right, just element dot right. Okay. All right. And then if it is null, what do we do? Do we need to do anything? Right, it's print element dot value, correct. Do we need to do anything or are we good here? Yep, you can just not do anything if it's null. Perfect. Now let's do pre-order. Public void pre-order. And then we're going to make the actual, this time private. All right. And so what do we do here? We're going to do the same check, right? And then what's the order now for pre-order?
I guess we should print first.
Print first. So you print element.value.
And then
Okay.
just make a recursive call to the left one and then a recursive call to the right one,
All right.
if I'm not mistaken.
Left and then right, or right and then left?
I think it's left then right, because usually like intuitively when I try to like go through pre-order, I always like, for example, like from my root, I go to the left, not the right. So I would start with left.
Okay.
Dia
right.
always says always left before right. What do you have to say to
Mhm. Pardon?
I said, what do you have to say to that for Dia saying always left before right?
Always left before right. Is that true? Why is that true? Yeah, it is always left before right. That's correct. And so what are we missing here? If anything.
No, I don't think we're missing anything. I think just like the in order traversal, like we're good. If it's null, then we just don't do anything actually.
Okay. And then what if we called this from a different class? Would it work?
I think it would.
Really?
Private.
We can try.
Well, no,
Okay.
it's a private class. I was looking at the implementation and forgot that it was a privately declared class.
Mm-hmm. So what are we missing here? Pre-order in the public method. That is correct. So we just do a little pre-order with this dot root. Implement pre-order. There we go. That's right. Now we can run it. And so finally, we have public void post order. And then we have our other one, our private class, void post order. This time we have element. And there we go. So we're going to do our regular check here. And then now what is the order? Left, okay. Left, right, and then print. All right, so we'll just copy these and then we print.
I'm having a bit of trouble like visualizing this one like conceptually.
Visualizing this one conceptually.
Yeah.
Okay, let me see if I can get a picture somewhere. We're gonna go through an example as well, but let me see this. Post order traversal. So this basically scans through all the nodes from the bottom to the top, kind of. So if you look up post order traversal, or I might be able to send a picture in the chat.
I think I have an idea. Like it goes like level from level, but like let's say we have a non-symmetric tree, right? Let's say the root has like a child, and then that's the end of the branch, and then like the other child, but like it continues like and other levels. Then what would the order be in that case? Like would you start from like the most bottom one? That's what I'm having trouble like understanding.
Yeah, so if they're all on the left or all on the right?
Say all in the
Either way,
right.
yeah, you start with the bottom because you don't print until you get to the end of it, until you get to the end of the right. So first you go to the left and then to the right, and then you print. So printing is the last thing you do once all of your recursions reach the end.
I see. So like, let's say we have a tree, like the root, like the left one has no other branches following that, and the right one has like other branches. Then like, would that print the like the left I guess the left node of the root, and then move on to like the bottom of like each branch is on the right one, and then like go up.
Yeah. So if you had one on your left and the rest on the right, or are you talking about none on the left?
No, like at least like one level on the left, like
One level on the left?
Yeah,
Yeah,
excluding the roots.
That would print the left one first, and then it would move on all the way to the bottom to the right one, and then it would move
that makes
all
sense.
the way up.
Okay, now I think I'm getting the intuition behind it.
Okay, good. There's a bunch of pictures online if you want to look at post-order traversal for different examples. But right now, we're actually just going to go test it quickly. And for this, I already have a pre-copied test that we're going to try out. So here we're going to call this test binary search tree. And create that public static void main. And then here, actually I have that. What we're going to do is get this working first of all. So here we're going to do a try catch around all of these. That is a lot. Can you send a test file? Yeah, once I'm done typing this out, then we can do it. Element exists exception. And then I'm just not going to do anything. Or, you know what? Why is this not working?
Isn't the syntax like declaring the type of exception and like given? Okay, I think yeah, that's what it is.
Yeah, I just forgot the name of the variable here.
Yeah, and then you just like print that one.
Yeah. Okay. How many items do we have here? We have 6 of them. So I'm going to make 6 of these. 1, 2, 3, 4, 5, 6. So this is the order. Then we got 10, 5, 5, 40, 1, 7, 50. So if we were to insert these, how would the tree look like if we were to draw it out? What would the root be?
The first value.
Mm-hmm. And then the 5, where would that go?
Left. No, I'm not sure. I would know. It's always left first, right?
Left first, or why is left first? Why would 5 go to the left? Exactly, because 5 is less than 10. And binary search trees work by placing the value that's less on the left and the value that's right on the right. And then 40, where would that go? What would it branch off of?
The right, because it's superior to the value of the root.
The right of the 5 or the 10?
The 10.
The 10, exactly. And then the 1? 1 is left of 5, 7. 7 is right of 5, and then finally 50. What would that give us? Right of 40. Okay. So now for the pre-order, can someone guess what that's going to print out if we printed that tree in pre-order?
Well, it would just go in like ascending order. So,
We're going ascending order.
what are the values? Yeah, it would be 1, 7. No, 1, 5, then 7, then 10, then 40, then 50.
Is that right?
Well, no, my bad. I think I'm confusing it with something else. That's not what pre-order is, right? No, it would print the I'm getting confused.
Thinking of the in order.
Yeah, that's in order.
Yeah. What about pre-order? Remember, it prints, then goes to the left. Prints goes to the left. Prints goes to the left. If it doesn't have a left, then it goes to the right. And then it prints goes to the left. Doesn't have a left, goes to the right. So what would that be?
Would it print 10 and then go to the left?
Yep.
It'll print 5, and then go to the left, it'll print 1. And then
Mhm.
there's no right in 1, so it'll go back to 5, no right to 5, so it'll go back to 10. And there's
No
a
right 5. It had
Oh,
the 7.
sorry, there was 7. Yeah, I forgot about that. So yeah, it'll print 7, and then 7, no left, no right, so it goes back to 5. 5 is done too, so it goes back to 10. And then 10, it'll check the right because it did the left. So it'll go to 40, no left. No, it'll print 40, no left. Then goes to right, which is 50, and then it'll print 50, no left, no right. Yeah.
Exactly.
Oh, that was confusing.
And then it's done. Goes all the way back up in the recursion and it finishes. That is correct. So, yep, Celine was right. And you were also correct. What about in order now?
Quick question. Would you like recommend, for example, let's say we have a multiple choice question in which it's just like a screenshot of the implementation of like adding nodes to a tree. And then like, what would the, how's it called? Like pre-order be, or like whatever order we're asked to like give the values as an answer to the question. Do you recommend actually like drawing the tree and like, you know, making it more intuitive than to
Definitely
like,
recommend that.
Okay.
I definitely recommend drawing the tree. If you're not allowed computers, that is. If you're allowed to use code, then I would code it out and be easier. But intuitively, I would draw a tree. And I recommend learning that too, just to get to know what the different algorithms are. It's pretty useful. And so what would in order be in this case? Oh, you can't code MC? Okay, in that case, I would definitely recommend drawing it out and then doing it that way. And then pretending that you're the algorithm.
Basically, I'm not sure if I explained this like, you know, previously, but like what we had for the midterm, like for the multiple choice questions is literally like a screenshot of the implementation. So like you can't actually copy paste the code to like quickly compile it and see what happens. And like we had to go through it like line by line to like try to spot a syntax mistake or something. And then basically compile the code in our mind and like try to guess what the output would be. The problem is we were only given 30 minutes to do all that for 10 different questions.
That's right. Yeah, that's how it is too. When you go back to school and do things on paper again, they're going to make you code on paper too. So enjoy this while it lasts.
That sounds like pain.
Okay. So yeah, in that case, I would definitely recommend drawing it. Easiest way, quickest way, easiest way to understand. So you know what? Before we run out of time here, I'm going to run these and then we're going to see all of the algorithms here. So this was our pre-order. So it goes 10, 1, 5, 7, 40, 50, which is weird because I believe it should be 10, 5, 1, 7. So there might be a mistake there. In our pre-order. Should be a 10, 5, 1, 7. It's because we're calling in order first. No. We're calling pre-order first. Well, in this case, we can go and debug. Let's go check out pre-order. Oh, you're actually right. That's what you meant. Okay, it was calling in order from the pre-order. Good catch. And then now it should work. There we go. Now we have 10, 5, 1, 7, 40, 50. For in order, we have 1, 5, 7, 10, 40, 50. And then here we have 1, 7, 5, 50, 40, 10. Does that look good to everyone? I'll send out this code. That is the tester so that you can try it yourself. This is the element exists exception. And I hope I can do all of binary. Looks like I can't. So I'm going to have to do binary up to the in order. Send that in first and then after, or even that's too much. I guess I'll just do this. Can I send the file? Yeah, I can send the file. Binary search tree. There we go. Are there any other resources online or perhaps a textbook apart from the multiple exams from previous years where you can find additional practice problems? Yes, there are. I recommend looking through all of the data structures that you need to know, like linked list, doubly linked list, queue, stack, binary search tree. Go to geeks2geeks.com. And then they have different things and different problem sets that you could do with those, as well as solutions to them. And so if you go through those and you think they're a bit too easy or a bit like you've already seen them before, you could then go to LeetCode and then choose relevant problems, and it's going to make you solve problems according to whatever data structure, whatever problem set that you choose. So if you need extra practice. And so, yeah, leetcode.com, whatever Omer said, and then Geeks to Geeks as well. They have really good resources, really good code follow-alongs and explanations to however the data structures look like. All righty. So we are done with this for now. But not done with the code, because what we're going to do is your past final. So Alay sent me this, and I believe that you should have it. I'll share my entire screen here just in a sec. Just like that. Is everyone able to see that?
Yep.
And does everyone have this problem set here? If someone doesn't have it, then Alay, could you just send it into the chat so that everyone gets it?
For sure. I'm actually going to send the link to the Piazza topic that was created by the professor that contains this.
Okay, perfect. So we're just going to go through this. And I'm going to create a new package called just ITI. There we go. We're going to do question 1 and question 2. And so to get started here, we're going to read this. So question 1, we're going to try to go through this fairly quickly. If we don't have time to do this, we'll move on to Discord because we have another Cookies and Cram session after this for another class. But here's the first question. A sparse vector is a vector of numerical values in which many entries have the value of 0. Such vectors find applications in data science and machine learning. Implementing a sparse vector using an array would result in inefficient operations and a waste of memory. Here, we propose a compressed representation using linked elements. Specifically, the implementation only stores the values that are non-zero. The values that are not physically stored in the list are all 0. The following examples illustrate the concepts as well as the intended behavior. First, a sparse vector of dimension 1024 is created. And so here what I'm going to do is I'm going to immediately create a class called testSparseVector. And then I'm going to create another class called SparseVector. And then for testSparseVector, what I'm going to have here is my main method. And then I have public, let's say test dimension right here. And then we're going to import and say sparse vector equals, or sparse vector v, we're going to copy down equals new sparse vector. And then here we have 1024 as a parameter. Of course, we haven't coded that in yet. But here we're going to do, we're going to print out the v.getDimension. And then that should give us 1024. As seen here, executing the above program will give the following output, 1024. And so the figure below shows the corresponding memory diagram. Initially, the list consists of only a dummy node. So we do have a dummy node here, and that's very important. You want to include that, and you don't want to just have a null. And as you can see here, something we want to pay attention to is that we have 3 pointers. We have the head pointer that points towards the node itself. We have a next pointer that's pointing out of the node back to itself. We have also a previous pointer pointing out of the node and to itself. And then we also have a value, an index here, which is -1 for dummy node, and then the value 0, 0. And so then we have now calling the method set 3 times will change the memory representation as follows. So we have index 21, that gives us index 21 here. Then we have v.set index 610, we set that to 2.2, shown right here. And then index 89 is 1.6. And that's between those because it's smaller than 610 and it's a bit larger than 21. So it keeps the indices. And that's something that you want to pay attention to. And then also notice where the pointers go. This is a doubly linked list and it's circular. So whenever it's at the end, it goes back to the dummy node. And whenever the dummy node is at the, whenever you're at the dummy node and you go previous, that goes to the end of the list. And then all the other nodes are connected back and forth, previous and next. And so here we're going to create another function for this set. We're going to do test set, and we do same thing here. Test set. Now we do v.set 21, and then we do 5.2. And then we copy that 3 times. V.set, here we do 610 and 2.2. And then here we do 89. And then, oops, I just turned my screen off. My bad. Can you guys still see the screen?
Yep.
1.6. Okay, perfect. And then we're going to do public test set for the next one, saying in this second example, a sparse vector of dimension 5 is created. The value at position 2 is 42. The contents of the sparse vector is then printed. Notice that the index of the first value is 0. So it starts at 0. That's a piece of information that you want to know. Right here, I'll highlight this. Yellow highlighter. First value is 0. And then second, we have value of position 2 is set to 42. And notice how you only put one element in. That means there's only one node apart from your dummy node. But then when you print it out, it gives you the zeros. So that's another piece of information that you want to pay attention to. One dummy node, but five prints, one for every every index in the dimension. So here we're going to test iteration, I'm going to say, or just test loop, we'll call it. Then here we're going to copy this again. And now we have w.set or v.set 2 and then 42 and then for long d equals 0. D is smaller than v.getDimension and d++. So you're iterating over it. And then you print v.get_d. So you're iterating over all the objects, and even if it's not in there, you print the 0. So that's something that you want to pay attention to. And another thing is, I think it said somewhere here, and if it didn't, then we notice that the indices are actually longs and they're not integers. So pay attention to that too. And then so finally in the third example, sparse vector of dimension long.max value. So again, long is the dimension and long is the index. And then max value is created. So we create another sparse vector. So we do public test max. Create. Here we're going to put actually 5 because we don't want to loop 1024 times. And here we do system.out.println v.get dimension. And then here we do long.max value. Are there any questions with this and why we did it this way? If there's not, we're going to go on to code our sparse vector. Are there any questions with how the sparse vector looks and the specifications for it?
I have a question.
Sure.
Does it store? Does it like store the indices in order? Like if you give, because I see that it gave 5.2, 2.2, and 1.6, but or not the indices, sorry, the values in order. Like it said that 21, 610, 89, but in the actual memory representation, it's like in order. So I was wondering if it was checking.
So no, this actually doesn't check because you can only, this is like an array. So you can only have one element at the same index. And the only time it would have to check that is if you have several of the same indices, which you don't. So when you set something and it's at the same index, say we set 21 2 times to 2 different values, the second one is going to overwrite the first one. And so for that, you don't need to check that the values are larger or smaller than each other, only the index.
Okay, and the index is the left or the right value?
The index is the left, and then the value is the right.
Okay, thank you.
Alrighty, so now we're actually getting on to the question. I don't know if you're actually going to be given this file, but if you're not, I like to write them. And as you're reading it, you write the code down. And it just helps with reading. It helps you be more careful when you're reading, and it helps you read everything thoroughly so you know exactly what you're going for. You are given the file? Okay, that's even better. But make sure you highlight things if you can, if you have a highlighter or a computer. Important information such as the position 2, set at 42. What does that mean? That means position 2 is the only one that contains a node in this case, and information like that. And so let's go on to create our sparse vector. So things that we know, we have a private long dimension. Our dimension is in long. We also have a private element. Again, we're just going to call this element or just a lem. Here in the question, it says create a lem. So we're going to have a lem, and we're going to call this the head or the dummy node. And then here we have to create a private class, a lem. And then here, let's read this. It says in the class's sparse vector, implement a nested class called a lem to store the values of the sparse vector. Notice that neither sparse vector nor a lem have a type parameter. Perfect, neither of these do. And so the list of elements always starts with the dummy node. That's one thing, which is used as a marker for the beginning of the list. The dummy node is never used to store data. As we see here, the data is 0 and -1. So the empty list is just made out of the dummy list only. And each element in the list stores an index of type long as well as a value of type double. So we know the index is type long. So here for private class lem, we know private index, private long index. And we know that we have a private value called private double called a value. Typing out what I'm saying now. And so here we also need a constructor. So what would we put as our constructor here?
This dot value, this dot previous, and this dot next.
This dot previous and this dot next. So that means we need a private double previous and a private long previous. Or no, that wouldn't work either, because you don't want indices as next and previous. You want a whole element, so the whole node. And so how do we know that just from looking at this picture right here, that we want to reference the whole node and not just a number?
I mean, that's just how, that's just the nature of a doubly linked list. Like you're always going to have an element that points to the previous element and the next one.
It is. But the way you know that just from the drawing is that
With
it
the
doesn't
arrows,
point
I guess.
inside. The arrow points to the node itself right here.
Yeah, that makes
But
sense.
say they wanted one parameter, for example, that points to the index for some reason. Then it would have its arrow going in to the node and it would point further inside.
I see.
But yes, you're correct. That is the nature of a linked list. Points to the node. So you have your private element, private elem next. All right, and then for the constructor, what do we do here?
Public lm. I guess the only parameter would be the value. No, the index too, right?
Right? Or just the value?
Well, no, just the value because, well, yeah, because like the location of the element in the doubly linked list would give us the index automatically. If that makes sense.
Does that make sense? Let's take a look at what we use here. So when we set, we see two values here.
Okay, yeah. So we're entering two different values. Then yeah, we should have two arguments to enter. So two parameters.
Two parameters.
I don't know why I
Okay,
just
so
got
long,
confused on that one.
yeah, no worries. Long index and then double value, and then
I feel like
this
that's definitely the kind of state of confusion I would enter in the middle of the exam.
Yeah, it happens. And then so here,
also like this dot prev would be equal to null. And this dot, well, no, because this is a circular doubly linked list, right?
yeah. And so that means we have two types of elements, right? What are the two types of elements that we have in this question? Or two types of node?
I guess standard elements and like dummy nodes.
Exactly, standard element and dummy nodes. And what I like to do here is I like creating two constructors for whenever I need either the standard node or the dummy node. So this one could just be the dummy node. And then so this dot previous could be this, right? Because it circles back. If you need to create a dummy node, it's going to be the first one. And you never get rid of it after. So then this dot next equals this as well. Would this work?
I think so.
Yeah.
Yeah. Or do we do this dot previous equals lm?
No, we're like within the constructor, then it should be this.
This?
Yes.
Why wouldn't we just put lm?
Because you're making like a non-static reference to no. Yeah, like it's just conventional.
Yeah, so Thulam is saying lm is just the class, and then the object or the instance would be this. It would be this, which is of type lm.
Yeah, exactly. Like you can't make like a reference to something that's like non-static. You gotta like create an instance of that object to like make a call to.
What if this was static? Then we wouldn't have We wouldn't have the option of this.
Yeah, we would not even
Right.
have a constructor in that case.
So then we have our different type of object, or different type of node, public lem long index, double value. And then this time we're assuming that we have our dummy node already. And so here we would have a lem previous, or a lem prev, and a lem next. We already have our dummy node. And we're just going to set these. So I'll copy this. And do previous and next. All righty. That sounds good. Let's see what the question wants. So the implementation for the question, the nodes of the list are doubly linked like we did in the implementation. The list is circular like we did here with the lem pointing it to itself. The reference previous of the dummy node points to the last node in the list. In this case, when you're creating the dummy node, non-dummy, when you're creating the dummy node, it is the last. So the previous would point to itself. And then in the empty list, the dummy node is the first and the last node of the list. And it references previous and the next points, and that points to the node itself. The last node is easily accessible because it's always the node preceding the dummy node. The header of the list does not have a pointer to the tail element. Okay. We always have access to our dummy or the head in this case. And as you can see here, head always points towards the dummy node. And that's how you know dummy equals head. No matter how many elements you put in here, dummy always equals head. Head always equals dummy. So next, we have our instance variables. We have the necessary instance variables with appropriate visibility as seen in class. So I'm assuming what you saw in class is that you want to keep these private, dimension and head, correct? How do you know that? You know that right here. These are your instance variables for the class. See that in the box right there. There we go, that's all we need. And then we're gonna do our sparse vector creation. So we're gonna do public sparse vector. Constructor has long dimension as a parameter. And then so what do we do here? We just do this dot dimension equals dimension. Pretty simple. Pretty simple question, gives you 3 marks. Instance variables give you 2 marks. Pretty good. Does anyone have questions about this so far?
I do have a question. So there's a dummy node, right? And it has like an index of -1 and value of 0. So is it something that we do in the constructor or not? Like to
Something that you do in the constructor?
Sorry?
Would it be something you do in the constructor?
I would guess so.
You guess so? Is that, so you would do that?
Yeah, I would do that in the constructor.
Okay. This dot head equals new lem. And then what would we put here?
I think the example said like the index should be -1 and value 0.
Exactly, just like that. What about the previous and the next? Do we need anything there?
No, because it's the first node, so it's the dummy node.
Exactly. And in this case, we made 2 constructors. You don't have to. Or actually, in this case, it would be the easiest to do that. Set the next and previous in the constructor. Yeah, so you just do this here. All righty. So next, we're going to have long get dimension. That's our next question. 1 mark, pretty easy. Return this dot dimension. Pretty simple. So this is where it gets a little bit more difficult. So we get, here I'm going to put public. Here I'm also going to put public void set long index double value. Okay. Okay. What is our edge case here? What's the first thing we need to check?
If the head is null.
If the head is null?
Yeah, so that would mean that I mean, no, that's not an edge case. That would be a base case.
I don't think that would be a case at all.
Oh, wouldn't it?
Head could never be null.
I mean, yeah, because we have a dummy node.
We have a dummy node here.
Yeah, that makes sense. I was thinking of like standard doubly linked lists. In that case, if the head is null, then you just like set the head to be the element you're trying to set.
Right. So yeah, exactly. And so what we're seeing in the chat here is first, we're going to check if the index is within the bounds or within the range of the dimension. So that's pretty easy. That's pretty easy as a first check. So if index is larger than this dot dimension, or index is smaller than 0, because you can't have a smaller than 0 index, here we're going to throw new index set of bounds exception. So here it's telling us to do just that. So what does this do? It replaces the value at the specified position in the sparse vector. So it replaces if it already contains that. And then the method throws an exception of type index out of bounds exception at the specified index when it's out of range, and when it's less than 0 and greater than dimension minus 1. So dimension minus 1 is what we're going to put. Yeah, index is greater than dimension minus 1. So we're going to make sure to preserve the property that is sparse vector does not physically store the values that are 0. And that means we can say if value is 0, we can just return. We're done. Don't need to do anything. We don't store it because everything is automatically 0 in a sparse vector. All righty. And then here we're going to put an exception index out of bounds. Just like that. And then we're going to put our index. There we go. All righty. So here, now that we're done our edge cases, if we're done them, what do we do?
The base cases?
The base cases? What's our first base case?
If the thing is empty, like you only have the dummy node, or no, is it a base case?
It's empty. How do we check if it's empty?
If you, I guess, only have the dummy node. Yeah, I don't know.
If you only have the dummy node, how would you check for that? Here's what I would do. I would create an lm current element, just because we're going to iterate over things when we set to see where we should put them. And I'm going to say equals this dot head dot next. Head is our dummy node. And then here, head dot next, if that also points to our dummy node, that's how we know we only have a dummy node in our list. So lm and then new lm is the one that we're going to put in. Equals new lm, and then we're going to have index and value. We don't have a next and previous here yet because we haven't chosen where it needs to go. And so here, to actually iterate through it, I'm going to make a while statement. So we're going to say while current lm is not this dot head. So if it's not the dummy node, then we do something. But if it is, then we just end or insert our element next. But while the current lm is not this dot head, so that means we have elements and we're looping over them. Now we need to check. What's our first case that we need to check? Because remember here that we store things in value of index from smaller to greater.
We check if the index of the current element is the same as the index we're trying to like set the element on.
So if current element index equals index, like that,
Yep.
then what do we do?
Then we would just replace the current element with the new element.
Current element dot maybe value equals value, right? That'd be the easiest way.
Yeah.
Yeah. Okay. And then since we're done here, we're only inserting one. We just break out of the while loop. No need to continue. All right. That's our first case. Next, what do we do? Remember, Rajveer, that head.previous will never be equal to null because of our constructor here. Head.previous will be equal to this, so to head, when it's empty. Otherwise, it's going to be looped back around to the end. So here, what do we do? Here's what I would do. I would check if the current element dot index is larger than my current index. Because if it is, that means I don't need to loop any further. I've already reached the spot that I need to be at, right? Does that make sense to everyone? Because they're in order. And so if we've reached the one that is larger, that means the previous one is smaller and not equal. That's the only case. So this means we're at the end. And so here, we need to place our element in. So with a linked list, first, what we want to do is manipulate the new element. We don't want to take any links out of the existing until we've got our element set to the correct previous and next. And my rule is always to work on new lm first. So new lm previous would now be the current lm dot previous. New lm next would be current lm dot next. Is that correct?
No.
No.
It would be current lm.prev.
Dot prev. So next would be prev and prev would be prev.
Yeah, that's how like you would doubly link each node. No, what am I saying?
So you're linking both next and previous to the same node.
No, that's not what it should be. I'm getting confused again.
So here, let's go through this example, right here. We see v.set61 is 5.2. So we set that right away. Then 610, we set that after, right? So now say we want to get to 89. So first, We loop over here. We check, is it smaller? Is it greater? It's not greater. So we move to the next one. The next one would be 610, right? In that case.
Okay, so
the
like the next of the current would be equal to the added node, and the prev of the added node would be equal to the current.
To the current, exactly.
Okay.
The current one. Correct. And then now what do we do? Our current one, pretend it's right here on top as a circle and it's connected. These ones are connected to each other. What do we do here? Here, we're gonna have to link up. So current alem dot previous equals new alem, right? Because it's right before it. And then we have to link up the previous one to the new one. How do we do that?
New alem dot next equals
We've already done new alem dot next.
yeah, my bad. So current alem dot next.
Current alem dot next, that would be, say this is 610, that would be dummy node again. Did we just lose reference to the previous one? Did we just lose reference to the previous one? I think we did. We lost reference to the previous one because we replaced it with a new alem. So before this, what we actually have to do is current alem dot previous dot next, because we still have that reference to the previous one, equals new alem. And only then can we get rid of the reference to the previous by replacing it with new alem. Is this clear? And then here, we're just going to break it. Because we're done. We're done with the loop. And then after, what we're going to do here is current alem equals current alem dot next. We're going to iterate over. Sounds good. So now what happens if current alem is actually equal to this dot head? So that means it's empty, or it's at the end. Pretty much do the same thing, but with the dummy node. So new alem dot next equals this dot head, right? Because it's at the end, pointing all the way back. New alem dot previous equals this dot head dot previous, which if it's empty would be head again. This dot head dot previous dot next is the new alem. And same thing, this dot head dot previous equals new alem. That's right, should have that. Good catch. And so here, once we're done with the set, we can test, actually we can't test anything yet because it doesn't print anything. But let's go on to the next question, as long as there's no questions about this. Is everyone clear with this question? Yes? Okay. So here, next, what we want to do is double get. So we do public double get long index. All right, so now we just want to iterate over it. But here it says it throws an array of type index out of bounds exception. If the specified index is out of range, less than 0 or greater than get dimension. So here we're just going to copy this again. Copy that, put it into here. And then we're just going to iterate over. So lem current lem equals this dot head dot next again. And then we do while current lem is not this dot head. Same way as we did before. If index equals current lem dot index. So if we've reached the number, then we return current lem dot value. And then we know that right after we change it to current lem dot next, here we know that if we haven't found it and we've gotten out of the loop, right, we haven't returned yet, then we're just going to return a 0.0. Because otherwise, if it's not in and it's within the dimensions, it's going to be a 0. That's what a sparse vector means.
Quick question. If like once we find the element at the specified index, can we just break from the loop?
Return breaks from the loop. It breaks from the whole method.
Oh, yeah. I actually missed the return statement.
No worries. Is that clear for everyone? So that's pretty much it for get. And then get L1 norm is the next question. So what this is going to do is sum the absolute values of all the elements. It's pretty easy. I'd say all we need to do is iterate. So then we do public double get L1 norm. So and then what this does is we iterate again. So we can just copy that. We don't have this. And then we have a result here. So double result equals 0. And then we just add to the result. Result plus equals current lem dot value. And then here we return result, which is a double. That just adds the values. Is this correct? Or am I missing something here? So this is correct. What if the number is negative? Would this still provide us with the correct result?
No.
No? Why not?
Because you're adding, there's an absolute value that you have to add.
There's an absolute value, that is correct. So we do math.abs on this value.
Not absolute value that you have to add, but like it should be absoluted. That's the equation that's given. Yeah. I was just
Right
explaining further, my bad.
Yeah. Yeah, so that's what we were missing for that. All righty. So next question is public iterator get iterator. And so this is going to return an iterator over the sparse vector, and that's our next question. So we're going to return sparse vector iterator that we're just going to create right now. And so for that, we need to create a new file, new Java class called Iterator, and that's an interface. So what that has is Boolean has next and double next, as we can see right here. And that's it for that. So then we create a private sparse vector iterator private class sparse vector iterator, which implements Iterator, the one that we've created. So here, I'm just going to implement these methods, has next and next, because implementing means you need to implement everything. And then you override them. Should it return new? Yeah, should return a new sparse vector iterator. That's correct. So here, let's see. What do we do for has next?
We check if the next of the current is the dummy node.
Here, what I would actually do is create return index is smaller than dimension -1. Right. So we should have a sparse vector here, just to know what we're working with. And we should also have long current index, because remember, when we're iterating over these, we want to include zeros, even if they're not in the doubly linked list. So we have to keep track of what the current index that we're at is. And so here, this returns has next. It returns current index is not this dot vector dot dimension -1. And this means we just haven't reached the end of it yet. And if we haven't, then we have a next. And so what I'm going to do here is I'm going to create a constructor as well. So sparse vector iterator. It's going to have sparse vector as its parameter. And then, so we're going to have this dot vector equals vector, and this dot current index equals -1, because that's going to be our first index. That's our dummy node. How's that so far? Are there any questions with this? All good? All right, so next, what we have for our next is kind of running out of time here. But so here we're going to have if we do not have a has next, then we're going to throw new out of bounds exception. Iterator has no next value. But if it doesn't, then we're going to create a double next value equals vector dot get current index +1. So remember, if there's no next or if there's no next value for the index that we're at, it's going to return a 0, because that's what we put our get function as. And that's what allows us to return the zeros here in order. Current index equals current index +1, or just current index ++, and then we return the next value. It's simple as that. Are there any questions with this? I have an error somewhere. Where is my error? Ah. Any questions with this? Nope. Okay, so if there's no questions with this file right here, we're done. And so what we can do here is we can fix these methods. First of all, we'll do void. What we'll put in our main method here is we're going to put test sparse vector test equals new test sparse vector. And then what we're going to do is we're going to test dimension first, test dimension. Then we're going to system print just to space it out. Then we're going to test set, which is the second one that we went to. And then system print again. And then we're going to test loop. And then we have test max. And that's given us an error for some reason. Get dimension, like that. All right, and then finally, what we have here is another one. So this is going to be testing the iterator. So public void test iterator, and v equals new sparse vector, just like that. v.set to 42. Iterator I equals v.getIterator. And then while I.hasNext, we're going to system out print I.next. And so as you can see here, this is a very generic iterator, and it allows anyone to iterate over our data structure without actually knowing how it works behind the scenes. And that's why iterators are super, super important. And so finally, we're going to test iterator. We're just going to run all these. And starting from the top, we're going to see if they work. So test set shouldn't really do anything. So what I'm going to do here is debug it. And we're going to use the debugger here to see what it's actually doing. So our first one returns 1024. The executing program should return 1024. Test dimension works. So next, we're going to go in our debugger, and we're going to create a sparse vector, dimension 1024. Here's our head, our dummy node. Previous is the same one, as you can see. So v.set 21, that's going to give next value of 21 and 5.2, as you can see right here. And then we're going to insert the 610. We're going to add 610 or set 610. So as you can see, we have our head, and then our head.next is the 21. And then our 21.next would be the 610. And then so we step over one more time. So that finishes with our 89. And so we see the 21.next gives us 89. And so that places it between the 610 and the 21. And then the 89.next will give us 610, exactly how we want it. And so for the next test, we can just run through these and see if we get the right outputs. So for this one, correct outputs. For the set, we don't really get an output, so it's empty. And then here, get dimension for long max value works. And then all the way at the bottom, here we see our outputs for the iterator. And so that shows us that our code for the sparse vector is working. So are there any questions with that? So we're running out of time here. And what I'm going to do is invite everyone to the site Discord. If you're not already in it, I'll send the invite. And that's where we're going to finish up, because I don't want to overlap with the next cookies and cram session that's going on right now. So I'm going to look for an invite. Yeah, so Alay has an invite. What we're going to do is go into the IEEE channel. I'll actually go in there right now, and that's where we're going to do the Kahoot and answer the second question as well. So if you guys want to meet me, I'm in there right now. And I'll start sharing the screen as well. So IEEE office hours channel.
Vlad, could you please share the how's it called? The code for sparse vectors and test sparse vector on the IEEE textual channel on the site Discord server?
Yeah, I can.
Thanks.
And so I'm going to end this here in a few minutes. Right after I share them. Sparse vector, test sparse vector, and then of course our iterator. And then IEEE chat. And you can just leave this if you're in there and you're ready. The IEEE channel. You know what? I'm just gonna start talking in there. Hey everybody, so we're in the Discord now. I'm gonna end the Zoom right now. And so yeah, join the Discord and we're gonna continue and finish off Cookies and Cram there. See you guys. I'll make Omer host and he can keep this alive.
All right, Ethan. I'm gonna close the meeting currently. If you're still hearing me, we are moving over to the EEX site server on the IEEE channel.